Your first 1,000 days on Mars would be a non-stop fight to not die. The air kills you in seconds, the cold bites through metal, radiation hammers you every hour, and every life support system around you is still basically experimental. In this video, you're the one on the surface, and we're going to break down step by step. Why just reaching day 1001 would be a miracle of engineering and human endurance. You hit the Martian atmosphere at more than 5.5 kilometers per second, around 12,000 miles per hour. The air is thin, the pressure is only about 600 pascals, less than 1% of Earth's sea level pressure of 101,325 pascals. That sounds gentle, but at that speed, it is not gentle at all. The gas in front of your spacecraft gets squeezed and heated until it turns to plasma. And all that heat has only one place to go, into your heat shield. You're betting your life on a few centimeters of material across the bottom of the spacecraft. If the calculations for the angle of entry are slightly wrong, you either bounce off the atmosphere and miss the planet, or you come in too steep and burn up. There is no pausing, no second attempt. The entire sequence from entry to landing is pre-programmed, because the radio delay to Earth is too long for real-time control. For about 5 to 6 minutes, every kilogram of your ship is trying to keep its shape while the atmosphere is trying to strip away energy and material at the same time. Temperatures at the shield surface can go well above what you see on the outside of a re-entering vehicle on Earth, because the air is thinner, so the shock layer behaves differently. If a tile or a panel fails, you do not get a slow warning, you just get a rapid rise in heat in places that were never meant to see it. You survive that and the speed drops, but now you face the next problem. How do you slow down the rest of the way when the thing you normally rely on, a parachute, barely works here at all? On Earth, parachutes are simple in concept. Pull a cord, open a big canopy into thick air, slow down. On Mars, at 600 pascals, the air is so thin that a parachute has to open while you are still moving at supersonic speed, at very high Mach numbers that would be considered too dangerous in Earth tests. The canopy has to be huge, like the 16-meter, 52-foot parachute used by the Curiosity rover, and even then it can only cut the speed part way. For a human lander, the mass is much larger than any rover. The forces on the fabric, on the suspension lines, on the attachment points are extreme. The deployment has to happen exactly right. If it inflates unevenly, if the fabric tears, if lines tangle, the parachute can fail instantly. If that happens, the first 1,000 days on Mars end in the first few hundred seconds. But even when the parachute works, it leaves you still falling too fast for a safe landing. So the next question hits you. What happens when you fire rockets close to the ground on a dry, dusty planet that has never seen a human spacecraft land this heavy before? In the last stretch of descent, maybe the last kilometer or less, you light descent engines. These engines are designed to work in low pressure, so their exhaust fans out into wide plumes. Those plumes slam into the surface and hit the loose regolith, the powdery dust and sand that covers Mars. The result is a violent spray of particles in all directions. You get a dense cloud of dust that can wrap around the lander, block cameras, confuse sensors, and sandblast exposed parts. On the Moon, we have already seen descent plumes carve holes under landers and kick rocks out at dangerous speeds. Mars has lower gravity, about 3.71 meters per second squared, around 0.38 g, so dust and rocks stay airborne longer and travel farther. You do not have a prepared landing pad on your first mission. You are landing on natural ground, which might be uneven, soft or layered, with different materials that respond unpredictably to the engine plumes. This means your landing legs, your sensors, even nearby cargo can get hit by debris in the very moment you are trying to touch down gently. The first crewed landers will teach everyone which designs can handle this and which fail. You are discovering it in real time. Say you get past that, and your lander is upright, the engines shut down and the dust starts to fall. You have not even stood up yet, and there is another issue waiting. How does your body handle 0.38 g after months in weightlessness, while you are exhausted and stressed? In orbit on the way to Mars, you've been in microgravity for months. In that time, your heart has adapted to pushing blood without any down direction. Your body has reduced blood volume, your leg muscles and back muscles have shrunk unless you trained hard every day, and your bones have started to lose density. On the International Space Station, astronauts can lose around 1 to 2% of bone mass per month without good countermeasures. Now, the moment you stand on Mars, your body suddenly has a clear down again, but only at about 38% of what it is used to on Earth. That sounds easy on your joints, but your cardiovascular system is trying to relearn how much pressure it needs to move blood to your brain and your feet. Your balance system in your inner ears is confused. You're in a pressure suit that adds a lot of stiffness and extra mass, making every movement harder. You have to climb down a ladder, stand on new ground, move cargo, maybe walk to an early habitat structure. All of this is happening with reduced strength, altered reflexes, and unfamiliar gravity. A simple stumble on the ladder or a bad step on a rock can turn into an injury that you cannot easily treat, this far from a real hospital. Behind all of this physical stress, there is still one more key question to answer on day 0. Once you leave your seat and step into your habitat, how safe is the place that is supposed to keep you alive for the next 1,000 days? Your ship and your first habitat are pressure vessels, not normal buildings. Inside, you'll want something around 70 to 100 kilopascals, because that lets you breathe and work in a roughly Earth-like environment, maybe with adjusted oxygen levels to reduce structural stress. Outside, Mars sits at about 600 pascals on average. The pressure difference is huge. The walls are thin, made of aluminum, composites and insulation, maybe only a few millimeters or a couple of centimeters thick. Think about what that means in practical terms. Every bolt pattern that holds 2 panels together is fighting a constant outward push. Every hatch is a controlled leak that must stay sealed. Every window is a high stress point where materials of different types meet. Any tiny manufacturing defect, any crack from launch vibrations, any seal damaged by dust during landing, can turn into an air leak. In the first generation of hardware, nothing has a long track record on Mars. You are living inside prototypes. Life support software is still on its early versions. Pumps, valves, sensors and filters have not yet run for thousands of continuous hours in real Martian conditions. When you first equalize pressure, open the hatch and move from the lander into the connected habitat modules, you are trusting that every part of that system behaves exactly as tested. So on day 0, you are not just landing, you're stress testing your heat shield, your parachute, your engines, your own body and your only shelter, all in one chain of events that cannot be stopped once it starts. You have survived gravity and hardware so far, but when you finally shut the hatch and look out at the red sky, one simple fact hits you. Outside that thin layer of metal, the entire atmosphere is unbreathable, near vacuum, and completely unforgiving. The next question is simple and brutal. How do you live for 1,000 days on a world where taking one breath of the outside air would knock you out in seconds and kill you in less than a minute? Breathing is the one thing you never think about on Earth, and on Mars it instantly becomes the most dangerous system in your life. The air outside your habitat is not thin but okay. It is basically a toxic, useless gas mix at the wrong pressure. About 95% carbon dioxide, around 2.7% nitrates, 1.6% argon, and trace amounts of everything else. Oxygen is around 0.13%, which is functionally zero for you. At the surface, the total pressure is roughly 600 pascals. That's 0.6 kilopascals. On Earth, you live at about 101 kilopascals with 21% oxygen. So the numbers are brutal. The partial pressure of oxygen on Mars, the oxygen slice of that 0.6 kilopascals, is tiny. Your lungs simply cannot pull enough oxygen molecules out of that mix to keep your brain alive, no matter how hard you breathe. If your helmet seal fails during an EVA, or a hose disconnects, you do not have minutes to solve it. In about 10 to 15 seconds, you start to lose consciousness, and within under a minute, you are dead. There is no take a deep breath and run back. There is no hold your breath. The air never helps you, not once, in your first 1,000 days. That is why every single step outside is done with checklists, with suit pressure checks, with constant line of sight to airlocks when possible. A casual attitude that might be fine on an Antarctic base would be suicidal here. One loose connector, one unnoticed cut in a glove, and the atmosphere finishes you before anyone can drag you inside. Losing oxygen is bad enough, but Mars adds a second brutal effect. What happens to the water in your body when the pressure outside drops far below what humans evolved for? Below about 6.3 kilopascals, something called the Armstrong limit, liquid water boils at normal human body temperature. Mars surface pressure is usually well below that value. Your body is mostly water. If your suit fails badly or you step into Martian air with no pressure protection, water in the exposed parts of your body starts to boil. Not like a pot on a stove with bubbles and steam you can see, but at the microscopic level, in your saliva, in the moisture on your eyes, in the lining of your lungs. You do not explode, that is science fiction. What really happens is your skin and tissues swell as dissolved gases come out of solution, your lungs cannot transfer oxygen or carbon dioxide properly, and your blood circulation collapses. Hypoxia, the lack of oxygen, still kills you, but now your organs are also taking damage from the pressure drop itself. This is why the habitat hull is not just a wall, it is a life support boundary more important than any building on Earth. On Earth, if your window cracks, you get wind and maybe rain. On Mars, if a window or a seam fails badly enough, the pressure in that room can crash toward Martian levels in seconds. And anyone inside without a mask or an emergency hood is in immediate danger. Even if you respect the air and the pressure, Mars still has another trick. The planet does have weather, but it is not the kind of weather your instincts understand. A strong Martian wind might reach about 30 meters per second, around 110 kilometers per hour, roughly 70 miles per hour. On Earth, that is serious storm territory, capable of knocking people over and tearing off roofs. On Mars, because the air is so thin, the force on your body is much lower, more like a firm breeze, so you might be tempted to think, fine, wind is not a big problem. The issue is not the push, it is what the wind carries. The atmosphere can pick up incredibly fine dust particles, micrometers in size, and keep them suspended for long distances and long times. These grains are small enough to get into every crack, every tiny opening around hatches and panels. They scratch visors, they coat solar panels, they foul radiators and filters. Sometimes that dust does not just blow around locally, it goes global. Planet-wide dust storms can raise the amount of dust in the air until surface sunlight drops by 80 to 90% for weeks. Mars already gets less sunlight than Earth, about 43% of the solar energy, and now a storm cuts that down even more. In your first 1,000 days, you are probably still relying heavily on solar panels and batteries, maybe with a small nuclear unit if you are lucky. A long dust storm pushes you right up against your power limits. You end up rationing electricity, slowing or stopping non-essential work, maybe even dimming lights in parts of the habitat to keep life support running. The air that would kill you in one breath is also your main resource for staying alive. So the next step is obvious and risky. How do you turn this carbon dioxide blanket from a poison into something useful? Carbon dioxide can be split into oxygen and carbon monoxide using high-temperature electrolysis. NASA's MOXIE experiment on the Perseverance rover has already done this on Mars at small scales, grams of oxygen per hour. For a human base, you need to scale that up to kilograms per Martian day. A sol, about 24 hours and 39 minutes. That means bigger solid oxide electrolysis stacks, more plumbing, more compressors to pull in thin air and feed it to the reactor, and a lot more power. Electrolysis is energy hungry. It wants steady, reliable electricity and steady temperatures. In your first 1,000 days, you are not running a big, mature industrial plant. You are running first or second generation machines in an environment full of dust, cold and thermal swings. You will spend a lot of time watching sensors, replacing filters, tuning flows, and updating software just to keep that oxygen output steady. Each time the system goes down unexpectedly, you start burning into reserves. Every restart is stressful, because this is not just a lab demo, this is the gas mix your crew is breathing next week. All of this is happening under a sky that breaks your Earth-shaped ideas about where space starts. On Earth, We talk about the Kármán line at around 100 kilometers, 62 miles, where the air is too thin for regular wings to work. On Mars, the atmosphere is already so tenuous at ground level that many of your Earth-based aerodynamic instincts fail. Drones can fly on Mars, but they need very large rotor blades and fast spin rates to generate lift in that thin air. Dust does not settle the same way as on Earth, because the particles are tiny and the drag is different. Convection, the way warm air rises and carries heat, is weaker, so heat moves differently around buildings, radiators and people. Even small fires in controlled lab setups behave in unfamiliar shapes because the flow of gases is different. To survive a full Martian year, including your first winter, you have to unlearn your normal expectations about wind, storms, cooling and flight. You have to replace instinct with data and procedure. The air above you is too thin to save you during descent, too toxic to breathe, too weak to carry familiar weather, but still thick enough to move dust, strip heat and interfere with power. You've learned that one breath of outside air is fatal, that the pressure can make your own body fluids boil, that weather is less about wind and more about dust and darkness, and that even your oxygen comes from a machine that can never really take a day off. But this is only the external layer of the problem. There is another invisible field constantly pressing through your skin and your bones on Mars, something Earth's thick air and magnetic shield normally protect you from. On Mars, that shield is gone, so the next question is direct. How does your body cope when the planet lets cosmic radiation and solar storms hit you almost unfiltered, every hour, every day, for your entire first 1,000 days? On Mars, gravity feels like it's helping you, but biologically it is setting you up for a slow, constant fight. Mars pulls at you with about 3.71 meters per second squared, roughly 0.38 g. If you have a mass of 80 kilograms on Earth, about 176 pounds, you feel like you're carrying only around 30 kilograms, about 66 pounds, on the surface of Mars. Walking feels lighter, climbing a ladder feels easier, jumps are higher, steps are longer. At first that feels like a superpower, but your muscles and bones are not cheering. They stay strong by handling load. On the International Space Station in microgravity, we've seen astronauts lose up to 20% of muscle strength and around 10% of bone density in some areas over only 6 months, if they do not follow strict exercise routines. Now think about your path. You already spent months in near zero G on the way to Mars, losing some strength and bone density. Then you slam into a world with only 0.38 G, and you immediately start heavy physical work, moving equipment, digging trenches, assembling habitats, using tools mostly designed around Earth gravity and human strength at 1 G. So your body is in a bad compromise. It's not weightless, so muscles and bones do get some loading, but it's far below what they evolved for. You're trying to do construction, mining and maintenance with a body that is already partially deconditioned and now is getting weaker more slowly instead of fully recovering. You will need aggressive workout schedules, resistance machines, maybe centrifuges for artificial gravity sessions, just to hold the decline to an acceptable level. Skipping exercise is not just being lazy, it's literally trading away your future ability to walk without fractures. If your weight changes but your skeleton still thinks in Earth units, what happens next is simple. Your bones begin to forget where they came from. Bone is not a fixed structure. It is living tissue, constantly being broken down and rebuilt, based on the forces you put through it. On Earth, even bed rest studies, where subjects lie still for long periods, show bone loss around 1% per month. Spaceflight data in microgravity is similar without countermeasures. Mars gives you more load than orbit, but much less than Earth. So in your first 1,000 days, your skeleton sits in a strange middle zone. You're not floating, but you're not fully loaded either. The signals your bones get from muscles and weight bearing are weaker. Cells that break down bone and cells that build bone are trying to find a new balance in this 0.38 G world. The long-term result is not fully known. You might see slower but still significant bone loss, changes in bone structure, and increased risk of fractures, especially in hips, spine, and legs. Now, add the terrain. You're not walking on polished floors, you're stepping on rough regolith, scattered rock slope craters, maybe loose dust over hidden holes. A stumble on a rock that would be just a bruise on Earth could be a serious fracture here. If your bones have thinned, and there is no level 1 trauma hospital within 225 million kilometres, about 140 million miles. Lower gravity also means you can fall in slow motion, but that can be deceptive. You hit the ground with less force, yes, but your weaker bones and altered reflexes might not handle even that reduced impact well. Every unnecessary fall is not just an accident, it's a medical event in a place where surgery and complex imaging are limited. Bones and muscles are one part of the story. Inside your body, your fluids and pressure systems are also trying to adapt, and they don't have a clear template for 0.38 G. In microgravity, fluids shift toward your head because nothing pulls them down toward your feet. Astronauts get puffy faces, thinner legs, and, more seriously, some get changes in eye shape and increased pressure inside the skull called intracranial pressure. A few come back with lasting vision changes. On Mars, partial gravity might reduce that effect, but it probably won't erase it. Your cardiovascular system is built for 1G, your heart muscle thickness, your blood vessel elasticity, your one-way valves, all evolved to push blood up from your feet to your brain against Earth gravity. In 0.38 G, the balance is different. Blood may pool in new patterns. Stand up too fast and you might still get a head rush or even faint, especially early on while your body is trying to recalibrate. Now put that system inside a suit. Outside work means a pressurized suit that adds mass, stiffness and effort. Just bending over or climbing a small slope in a suit can drive your heart rate up. Your body is trying to figure out circulation in 0.38 G. At the same time you are loading it with physical labour, thermal stress and psychological stress. For the first 1,000 days, you and your crewmates are essentially a live medical study on how human circulation and neurovestibular systems adapt to partial gravity. You will be drawing blood, doing ultrasound scans, running on treadmills, tracking vision changes, and sending the data back to Earth. There is no big sample size, you are the sample size. While all that is going on inside, Mars gravity is also setting up a more direct kind of danger. How you move heavy objects and how your instincts mislead you. Take a 100 kilogram component, maybe part of a habitat shell or a piece of heavy equipment. On Earth, that's a serious lift, about the mass of a big motorcycle engine. You need tools, maybe a hoist. On Mars, under 0.38 G, it weighs about 38 kilograms, around 84 pounds. You can push it, pull it, maybe even lift parts of it with much less effort. It feels manageable. But mass does not change. The inertia stays 100 kilograms. Once you get that object moving, it wants to stay moving at the same speed and direction, just like it would on Earth. Your nervous system is tuned for 1G, so your reflexes, how hard you push when you expect something to slow down, are based on a lifetime of Earth experience. In 0.38 G, you are likely to push too hard or not brace enough or misjudge how fast a rolling or swinging object will stop. That combination, lighter weight plus unchanged inertia, is a classic trap. The first serious construction accidents on Mars will probably not be from fancy new technology failing. They will be from basic physics playing against Earth-trained instincts, a crate sliding farther than expected, a crane load swinging wider, a habitat tank bumping into someone who thought they were clear. And with lower bone density and no full hospital, a simple broken leg or crushed hand can turn into a life-changing or even life-ending event. All of this is about adults who grew up in 1G and then moved to 0.38 G. There is a bigger, longer-term question sitting behind that. What happens if someone never sees 1G at all? If Mars becomes a real colony, at some point, people will think about pregnancies and children born under Martian gravity. But during your first 1,000 days, that idea is almost certainly off the table. Right now, we have good data for development in 1G and some data in 0G from animal studies and short space missions. We have almost nothing solid for long-term growth in partial gravity like 0.38 G. You do not know if a fetus can develop a normal heart, bones, and brain wiring in that field. You do not know how childhood growth plates in bones respond when the load is always lower. You do not know if a person who grows up entirely in 0.38 G can ever safely visit 1 G without major health problems. So early missions will write strict rules. Pregnancy will be banned, not just as a social policy, but as a medical and ethical decision. You cannot run human development experiments on children in an environment you barely understand. For now, Mars is for adults who chose the risk, not for kids who had no say. So in these first 1,000 days, gravity is not a simple number like 0.38 G. It is an ongoing force quietly changing your muscles, your bones, your blood, your balance, your work safety, and the entire plan for future generations. You feel lighter, but the hidden load on your biology is heavier than anything you trained for. And all of this is happening while another invisible stressor is hitting you every moment you stand on the surface or even inside a lightly shielded habitat. High-energy particles from space slamming through your body because Mars no longer has the protection Earth gives you for free. The next question is blunt. How do you build a life on a planet where just existing for 1,000 days means taking a radiation dose that can push you toward your lifetime limits before you even think about going home? On Earth, radiation is something you mostly ignore because the planet does such a good job of blocking it for you. On Mars, that protection is basically gone. Earth has a global magnetic field and a thick atmosphere. Together, they bend and absorb a huge fraction of the high-energy particles coming from the Sun and from deep space. Mars used to have a magnetic field, but it lost it billions of years ago. What's left now is a patchy, weak magnetic environment and a thin atmosphere that, in many places, gives you only about 20 to 30 grams per square centimetre of shielding overhead. Earth's atmosphere, from sea level up to space, gives you on the order of 1,000 grams per square centimetre. That is a huge difference. Satellites and rovers have already measured radiation on and around Mars. The numbers they see on the surface are roughly 0.6 to 0.7 millisieverts per day. On average, that is a dose rate, the amount of radiation energy your body absorbs. Over 1,000 days on the surface, that stacks up to somewhere around 600 to 700 millisieverts. And that does not include the cruise out and back, where levels can be even higher because you have almost no shielding. This is not instantly fatal. You're not going to drop dead from that alone, but it is absolutely not harmless. It is enough to move your lifetime cancer risk, enough that agencies like NASA worry about the limit a human should take across an entire career. On Mars, you start burning through that budget just by sleeping in the wrong place for too long. To understand how extreme that is, put it next to what you're used to. On Earth, natural background radiation from rocks, cosmic rays that do reach the surface, and small amounts in food and air typically add up to around 2 to 3 millisieverts per year, depending on where you live. That is per year. On Mars, you are taking something like 100 times that dose every year if you just stand unshielded on the plane. Even in low Earth orbit on the International Space Station, where Earth's magnetic field still helps a lot, astronauts see around 80 to 160 millisieverts over 6 months. People already treat that as a serious occupational exposure. A full Mars mission with months of travel, 1,000 days on the surface and then the flight back can easily approach or exceed current career limits, especially if solar activity is not in your favour. So by agreeing to go, you're accepting that your lifetime cancer risk is going up in a way you can measure on paper before you even see the rocket. There is no way around that. You can reduce it with shielding and smart mission timing, but you cannot bring it down to Earth levels. That is the background exposure, the constant drizzle. Then there are the spikes, and those are what really keep you watching the space weather reports. The slow background dose mostly comes from galactic cosmic rays, extremely energetic particles from outside the solar system. On top of that, the Sun occasionally throws tantrums called solar particle events or solar storms. These are bursts of high-energy protons and other particles launched out by solar flares and coronal mass ejections. In a big event, the radiation level can jump by 2 orders of magnitude, meaning up to 100 times higher for several hours or more. On Earth, our magnetic field and atmosphere absorb a lot of that. On Mars, with its weak shield, Many of those particles can reach the surface with enough energy to cause acute radiation sickness if you are unlucky and unprotected. The difference between a dose that just adds to your long-term risk and a dose that makes you sick right away can be only a few centimeters of shielding material over your body. In your first 1,000 days, your base is new. You do not yet have multi-meter thick underground bunkers everywhere. You probably have a couple of dedicated storm shelters, small rooms surrounded by water tanks, food stores, batteries, anything heavy you can cram around them. You have some sandbags or boxes filled with regolith. When the space weather monitors see a big solar event starting, you get a warning with some lead time and everyone drops what they're doing, goes inside and squeezes into those small dense spaces. The early years on Mars will include drills where you practice that. They will also include the first real events, where you sit in a cramped cube, listening to the storm reports, knowing that meters away, outside the shelter, the radiation level would be high enough to damage your bone marrow or your gut lining. Those are the moments where you really feel how thin your protection stack still is. To push that risk down, you turn to the planet itself. The soil that gets into everything can also save you. Radiation is blocked by mass. It does not care much what the mass is. Up to a point, it just matters how much material the particles have to pass through. A rough rule of thumb is that 5 to 10 grams per square centimetre of extra shielding can significantly cut some components of the space radiation environment. Martian regolith has a density that means putting 1 to 2 meters, around 3 to 6 feet of it over your habitat, can dramatically reduce your exposure. That is why later colonies will probably be underground, maybe in lava tubes or trenches, with thick roofs of soil and rock. They might also use engineered shielding made from processed regolith, water, plastics rich in hydrogen, and other materials tuned to block specific particle types. But you are not later colonies. You're early. In your first 1,000 days, you are likely to arrive to prefabricated habitats that are only partially buried, or maybe not buried at all on day one. One of your major construction jobs is to drive excavators, bulldozers, or specialized robots in low gravity, move huge volumes of dust and rock, and gradually turn a row of metal cans into something that looks more like a bunker. You're trying to outrun the radiation stats by getting enough mass above your head before time and random space weather catch up. Even if you stack all that dirt and wrap yourself in plastic and water and metal, there is still a hard problem no one has fully solved yet. What exactly does this special mix of radiation do to human biology over decades? Most of the medical data we have about radiation risk comes from X-rays, gamma rays, nuclear workers, and atomic bomb survivors. Those are different radiation fields than what you get in deep space or on Mars. Galactic cosmic rays include a lot of very high-energy heavy ions with high linear energy transfer, which means when they pass through tissue, they dump a lot of energy in a dense track. That kind of damage is harder for cells to repair correctly. We can model DNA breaks, estimate cancer probabilities, and run animal tests, but there are still big uncertainties. How does constant low to moderate exposure to this specific mix affect your brain over decades? Does it change the rate of neurodegenerative disease? Does it subtly affect fertility, or immune system strength, or lifespan in ways we have not seen yet? When you live on Mars for 1,000 days, you're not just another crew. You're a data set. Your blood samples, your MRI scans, your cancer screening results years later, all of that will be studied to refine the risk models. You are part of the first real multi-year trial of human life under Martian radiation conditions. The full outcome will only be visible long after the mission is over. So while you're trying to build a base, learn the terrain and run science, there is a constant invisible background process going on, particle by particle, track by track inside your cells. You're relying on thick enough walls, deep enough soil, and well-timed storm shelters to keep that process inside acceptable limits. And even if you solve that, even if you dig deep and build heavy, another set of physical challenges is always pressing in from the outside. The air is thin, the radiation is high, but the planet itself is also bitterly cold and covered in dust that attacks your machines and your lungs at the same time. The next problem is very physical and very simple. How do you keep yourself, your equipment, and your power systems alive on a world that behaves like a giant dusty freezer? where the air cannot carry much heat and the surface tries to strip energy and grind your gear down every single day. Mars is not just cold, it is cold in a way that never lets you relax. Average temperature across the planet is around minus 63 degrees Celsius, about minus 81 Fahrenheit. In the mid-latitudes at night, you can easily drop below minus 100 degrees Celsius, around minus 148 degrees Fahrenheit. Your suit, your habitat, your vehicles, every cable and pipe are constantly fighting that temperature difference. Inside your habitat, you want something like 20 to 24 degrees Celsius, around 68 to 75 Fahrenheit. That means the walls are holding a gradient of well over 120 degrees Celsius, more than 200 degrees Fahrenheit, across just a few centimeters of structure and insulation. That gradient never switches off. You are dumping heat to the outside 24/7, and the outside is trying to suck it away as fast as physics allows. Every watt of heat you generate is part of your energy budget. The power you put into heaters in the floor, into warm air circulation, into keeping water lines above freezing is power you are not using for mining ice, growing food, or running labs. A tiny leak in insulation, a bad seal around an airlock, a cable penetration with poor foam fill becomes a permanent drain that you pay for every single soul. Vehicles have the same issue. Rovers left outside overnight need active heating or careful thermal design, so their batteries and electronics don't drop below safe limits. You cannot just park something, turn it off, and expect it to work perfectly the next morning. Warming up hardware on Mars is not a 5-minute idle. It can be an hours-long process where you nurse components through safe temperature ranges. The cold also does strange things to the atmosphere itself, and that hits your hardware in ways you do not see on Earth. At high latitudes in winter, carbon dioxide in the Martian air literally freezes out onto the surface as dry ice. The atmospheric pressure drops, and you get seasonal caps made mostly of frozen CO2. Anything exposed in those environments has to handle not just low temperature, but direct contact with dry ice and repeated freeze-thaw cycles. Valves, hinges and seals can jam as thin films of condensed gas or frost lock moving parts together. Lubricants that work fine at minus 20 Celsius, minus 4 Fahrenheit, can thicken or fail completely at minus 80 Celsius, minus 112 Fahrenheit. Metals contract, changing tolerances. Plastics go from flexible to brittle. Rubber that would bend on Earth can crack like glass after enough cycles. You're not designing for a cold day in Alaska. You're designing for a regime where standard Earth materials approach their limits. Some greases solidify. Some solders creep and crack. Insulation foams shrink and separate from the walls they were glued to. In your first 1,000 days, almost everything you're using is first-generation or maybe second-generation Mars hardware. Lab tests on Earth try to predict how it behaves, but the real test is out here. With real dust, real temperature swings, and no quick reevaluation, you will find out which designs were wrong the hard way. While the temperature is trying to freeze you in your machines, the dust is attacking a different part of your survival, your power. Martian dust storms are not like the movie storms that knock over rockets. The air is too thin for wind pressure that strong, but optically they are brutal. The amount of dust in the air, often described by an optical depth value, can rise high enough that sunlight at the surface drops to 10 to 20% of normal for weeks. Mars gets about 590 watts per square meter of solar power at the top of the atmosphere, compared to roughly 1,360 watts per square meter at Earth's distance. So you start with less sunlight. Then a storm moves in and removes 80 to 90% of that. A solar array that might give you, say, 80 to 100 watts per square meter at local noon in clear conditions can suddenly be down in the single-digit range. Later, mature bases will rely more on nuclear reactors and large energy storage farms with serious redundancy. In your first 1,000 days, you might have one small fission unit if launch constraints allowed it, plus a lot of solar panels and batteries. A long, dense dust storm turns into a slow crisis. You watch charge levels drop, you shut down non-essential systems, you dim greenhouse lights, you pause heavy industry, you delay science tasks. Every extra cloudy sol forces another round of cuts. The same dust that blocks your power also goes after the machinery itself. All day, every day. Martian dust is not like talc from a store. The particles are tiny, sharp, and tend to hold electric charge, especially when they rub against each other in storms, a process called triboelectric charging. On the Moon, Apollo astronauts reported dust that scraped into seals, stuck to suits, and irritated lungs. Mars dust is similar in size and sharpness, but with an added problem. The soil includes chemically reactive compounds like perch laurets in many regions. This dust will get into everything. Filters clog faster than planned. Radiators slowly lose efficiency as layers of dust build up. Moving parts in suit joints and rover wheels grind down as abrasive particles chew on bearings and seals. Connector pins get coated. Solar panels lose output as a fine film builds up, not just during storms but during calm days as well. Every EVA you do in the first 1,000 days brings dust back in on suits, on tools, on samples. Airlock systems try to knock it off with brushes, air jets, or electrostatic devices, but nothing is perfect. Over time, dust-related wear becomes a major maintenance load. You're constantly cleaning, swapping parts, and redesigning procedures to slow the damage. Replacement bearings, seals, and filters are limited. If you run out early, some equipment simply dies. At the centre of this, there is one more balancing act that never stops: your own body heat versus the Martian cold. Your body at rest outputs on the order of 100 watts of heat, more when you work hard. On Earth, a lot of that heat leaves through convection, warm air rising off your skin and clothing, and through evaporation of sweat. On Mars, the air is thin, the pressure is low, and convection is weaker. In a suit at minus 60 degrees Celsius, about minus 76 degrees Fahrenheit, your life support system has to carefully move heat away from your body so you don't overheat in your own insulated shell, while also making sure your fingers and toes don't freeze. If your cooling system pulls heat too fast from your skin, your sweat can get too cold or freeze in layers, and your extremities will go numb fast. If it pulls too little, you overheat, your core temperature climbs, and you risk heat stress even while the outside world sits at minus double-digit temperatures. On top of that, low pressure changes how sweat behaves and how fluids evaporate. Engineers can test suit systems in vacuum chambers and cold rooms on Earth, but those tests do not fully capture partial gravity, real Martian dust, and real EVA workloads. The true behaviour only appears after hundreds of hours of real use on the surface. Until you've pushed through a few Martian winters, cycled suits through repeated cold-hot-cold patterns, and watched how materials age, you do not actually know which designs will quietly fail on you. So during your first 1,000 days, the planet is hitting you from 3 directions at once: extreme cold that never stops draining your heat, dust that blocks your sunlight and chews up your machines, and a thin atmosphere that cannot carry away heat or protect you. You survive only if your thermal control, your mechanical design, and your power planning all stay tight. But even if you manage to keep warm, keep the lights on, and keep your machines moving, you're still missing one core ingredient of life. You need air to breathe, water to drink, and systems to recycle them almost perfectly, because you cannot ship enough from Earth. So the next problem is ruthless and unavoidable. How do you build life support loops that close tightly enough that you don't slowly run out of air, water, and margin long before you hit day 1000? On Mars, life support is not a background system, it is the main job. Look at the numbers. One adult needs roughly 0.8 to 1 kilogram of dry food per day. You need around 2 to 3 litres of drinking water, plus several more kilograms for washing, cooking, cleaning, and system losses. Stretch that over 1,000 days and you're looking at something like a metric ton of food, and over a ton of water per person if you tried to bring it all from Earth. That's more mass than a small car, just to keep one person eating and drinking. Now multiply that by a crew of 6. You're not launching a mission anymore, you're launching a small supermarket and a tanker. The rocket equation punishes every extra kilogram, so you do not have the choice to be wasteful. You're forced into closed-loop systems long before they are fully comfortable or fully proven. That means your daily life is basically a mass budget spreadsheet made real. How much water is in storage, how much is in pipes, how much is in urine tanks, how much is bound in plants and food. You track it all, because losing a few percent here and there is the same as throwing years of safety margin out the airlock. Water is your first big loop and the numbers are strict. You need to recover more than 90%, ideally closer to 95 or higher. On the International Space Station, the water recovery system can already reclaim over 90% of water from humidity, urine, and other waste streams. That's in low Earth orbit with regular cargo runs, no dust, and controlled temperatures. On Mars, you need at least that performance while dealing with dust in every seal, bigger temperature swings, and no quick rescue if something fails. Your water loop has filters, pumps, membranes, and reactors. It condenses moisture from the air, filters wastewater, distills or runs it through multi-stage systems to remove salts, organics, and microorganisms. The oxygen you breathe likely comes from electrolysis of this water and from splitting CO2 from the Martian atmosphere. That's yet another set of pumps, compressors, solid oxide cells, and electronics. Any one of those pieces can fail. A pump bearing can seize from dust, a membrane can clog, a sensor can misread and shut down a critical unit. One failure may be manageable, but failures tend to cascade. A water processor going offline means less feedstock for electrolysis, which means less oxygen, which pushes you toward emergency reserves. On Mars, we'll fix it tomorrow can very quickly become, we run out of air in a few hours if this doesn't restart. So you design with redundancy, 2 pumps in parallel, spare filters, backup control boards. But every kilogram of backup you flew is a kilogram you did not use for more food, more shielding, or more tools. You're always trading safety in one loop against capability in another. You also have to decide how much of your life support will be purely mechanical and how much will be biological. You can scrub CO2 from the air with solid chemicals or machines like regenerable absorbers. Those systems are compact, predictable, and relatively easy to model. Or you can grow plants and algae that eat CO2 and release oxygen. Biological systems give you food, they help with air, and they can feel psychologically important. But they bring their own kind of failure modes. Plants need light, nutrients, stable water, and controlled temperature. Algae tanks need mixing, gas exchange, and careful monitoring. In closed spaces, you can get mold outbreaks, weird biofilms, or pests you didn't even know you brought with you. A fungal problem in a greenhouse can suddenly wipe out a big fraction of your food and your CO2 processing capacity at the same time. So early on, your colony is running both sides. You have mechanical scrubbers for baseline safety, and biological experiments to see how far you can push living loops. You're running hydroponic racks, maybe some aeroponics, algae photobioreactors, and microbial bioreactors to help break down waste. All this is happening under 0.38 G, with higher radiation and a different day-night cycle than Earth. You're basically running a huge systems biology experiment where failure doesn't just mean a bad paper, it means food shortages or air that drifts out of spec. And then there's the thing nobody likes to talk about, but you absolutely cannot ignore. Waste. On Earth, you flush and forget. On Mars, human waste is nitrogen, phosphorus, potassium, trace elements, and organic carbon. Exactly the stuff your plants need. Throwing it away is insane, but using it wrong is dangerous. You can't afford to just store it forever, and you can't afford for a pathogen to spread through your crew or your food system. Composting in 0.38 grams will not behave exactly like composting in 1 gram. The way gases move through a pile, the way microbes grow, the way heat distributes, all are slightly different. Your air is fully closed, so any smell or gas from a bad compost batch ends up in the same volume you breathe. You have a limited set of starter microbes and you're under constant radiation. The microbiome of your habitat isn't going to match any place on Earth. So you're running controlled waste processing, maybe high-temperature composters, maybe anaerobic digesters to make biogas, maybe chemical treatment steps. You're monitoring for pathogens, tracking nutrient flows, and testing outputs carefully before they ever touch your food production systems. Every gram you flush is either a future fertilizer input or a potential health problem. There is no out of sight, out of mind. On top of the hard physics and chemistry, there's an ugly statistical reality working against you. Most complicated systems do not fail evenly over time. Engineering data shows something called the bathtub curve. Early in a system's life, the failure rate is high. Then it drops and flattens, then rises again at the end of life. The early failures are often manufacturing defects, software bugs, or design oversights that show up only when hardware sees real use. This is called infant mortality for hardware. Your first 1,000 days on Mars are sitting right in that high-risk zone. Pumps that looked great in vacuum chamber tests burn out under constant dust exposure. Valves that cycled fine a few hundred times in the lab seize after a few thousand cycles in real Martian cold. Sensor glitches produce bad data that triggers the wrong automatic response in your control software. Later settlers will get version 3 or version 4 of these life support modules, redesigned after your mission reports came back with failure patterns and near-miss stories. You in the first wave are using version 1 and version 2, the bleeding edge. That means you spend a huge amount of your time not on exploration or science, but on maintenance, diagnostics, and emergency workarounds. Every time you fixed a pump with the last spare part or patch a leaky seal with improvised materials, you're pushing the curve forward so the next crew faces fewer surprises. But it also means your own 1,000 days are mechanically and biologically the riskiest phase in the entire history of Mars settlement. And all of this still assumes you have one more key ingredient under control, a reliable source of water you can feed into those loops. If you can't ship it, you have to dig it out of the planet itself, in a place where ice doesn't melt like it does on Earth, and where almost everything about the chemistry is new. So the next real question is this: how do you turn a dry, frozen desert into hundreds of thousands of litres of clean water, fast enough to drink, grow food, and run life support before your ship supplies run out? Mars looks dry, but your survival depends on the fact that underneath that dust, it isn't. Orbital neutron spectrometers and ground-penetrating radar have mapped large amounts of subsurface ice, especially near the poles and in some mid-latitude regions. Some estimates say that if you melted all that ice and spread it evenly, you could cover the whole planet in tens of meters of ocean, dozens of yards deep. That sounds like more than enough for any colony, but that water is not a handy lake or a flowing river. It is locked up as hard ice mixed with rock, or as pure layers buried under regolith. It's frozen solid at temperatures far below anything you normally deal with on Earth, and often sits under unknown thicknesses of dust and stone. Your first 1,000 days are not about exploring pretty ice cliffs. They're about turning that geological fact into a controlled, continuous source of drinkable water, without the benefit of huge mining trucks, full-size refineries, or an army of workers. You arrive with a limited set of drills, heaters, pipes and tanks, and you have to turn a patch of frozen dirt into a literal lifeline. So how much water do you actually need to pull out of the ground to stay alive and grow? The answer is a lot. Even with aggressive recycling, you're not running at camping levels of use for 3 years straight. A realistic target is something like 30 to 50 litres of water per person per day, when you add up drinking, food preparation, rehydrating stored meals, personal hygiene, cleaning, and inevitable system losses. That's about 8 to 13 gallons per person per day. For a crew of 6 over 1,000 days, you're looking at roughly 180,000 to 300,000 litres of water. That's 180 to 300 cubic meters, or 47,500 to almost 80,000 gallons. You're not shipping that from Earth. The mass would be in the hundreds of tons, so you have no choice. You drill, you heat, you melt, you purify. Every cubic meter of ice you recover, about 1,000 litres or 264 gallons, weighs a metric ton, a little over 2,200 pounds. In practical terms, you're running a small-scale mining and refining operation every single day, just to keep showers short and coffee real. Ice is now one of your main ores, and water is your most important product. On Earth, extracting ice is simple. Warm it, it melts. On Mars, the low pressure turns that simple picture into a more complicated job. At the surface, with pressures around 600 pascals, ice can skip the liquid phase and go straight from solid to vapor. That's sublimation. If you just heat an exposed ice deposit, it may not form an ice-liquid pool. It may just turn into water vapor that disappears into the near vacuum atmosphere. So your melting process often looks more like this. Enclose the ice zone as much as possible, heat it carefully, let water molecules turn into vapor inside a controlled space. Pull that vapor into pipes, then condense it back into liquid in a dedicated chamber. That means you are basically running a big dehumidifier inside a freezer, using pumps, heat exchangers and condensers, and you're doing it while the ground around you is at temperatures that can destroy normal equipment. You have to capture as close to 100% of that vapor as you can, because any leak out to the open air has lost water. At the same time, you have to keep your hardware warm enough to function but not so hot that you damage surrounding structures or create unstable ground under your equipment. Everything runs on power, which is limited, so you have to choose how much energy goes into pulling up new water versus how much goes into heating the habitat, charging batteries, and growing food. Even when you succeed at pulling water out, the job is not done. The raw melt or condensate is not guaranteed to be clean. Martian soil, and probably some of its ice, contains salts, including perchlorates, which are chlorine-oxygen compounds. In high doses, those are toxic for humans and for many plants. You cannot drink that water straight from the ground. You cannot just pour it into hydroponic tanks and hope the tomatoes sort it out. So you push the raw water through purification steps, filtration to remove particles, ion exchange or reverse osmosis to strip out dissolved salts, maybe chemical treatments or advanced oxidation to handle organics and perchlorates. Each of those steps needs membranes, cartridges, chemicals or power. They also create waste streams you have to manage, brines loaded with unwanted compounds that you cannot simply dump wherever you like, because your base is small and your environment is closed. Later in the colony's growth, those same perchlorates might be valuable as oxidizers in propellants or feedstock for chemical manufacturing. In your first year or two, they are just another chemistry headache in a system that has never been run continuously for 1,000 Martian days in real conditions. You are learning how often filters clog, how often you have to swap membranes, how your purification stacks respond to changing input quality from different drilling sites. There is no long-term operations manual. You're writing it by doing the work. Once you have clean water, you store it, and here Mars gives you one more twist. Water is not just something you drink, it's part of your structure and your shielding. Water is an excellent radiation shield. Around 10 grams per square centimetre of water can significantly reduce some components of the radiation field. In simple terms, a 10 centimetre thick layer, about 4 inches, across 1 square metre is roughly a ton of mass, and it does a real job slowing down particles. So your storage tanks are not just barrels in a corner, they become walls. You stack water around sleeping areas, storm shelters or control rooms. You use flexible plastic or composite bladders, arrange them as inner liners in certain sections of the habitat, and run controls to keep them at safe temperatures so they don't freeze solid or rupture. In theory, future colonies might take this much further, building ice domes, translucent radiation shields made of frozen water, underground bunkers wrapped in chilled water channels, all integrated into architecture. In your first 1,000 days, you are doing the crude version. You pump water into bags, barrels, and tanks, wedge them where they add the most shielding, and hope the materials survive the temperature swings and mechanical stresses. A crack in a tank is not just a leak, it is lost drinking water, lost shielding, and another repair job you did not have time for. So your relationship with water on Mars is very different from Earth. On Earth, it falls from the sky, flows in rivers, and sits in giant lakes. On Mars, every litre you drink has been drilled, heated, captured as vapour, condensed, filtered, chemically cleaned, pumped, stored, maybe moved again, and then finally poured into a cup. Behind that one cup is a chain of machines, pipes, and power lines that all have to work. And water is only one part of the story of staying alive. Turning regolith and thin air into reliable supplies is hard enough, but none of it matters if you cannot turn those supplies into calories. Food is heavy, hard to ship, slow to grow, and tightly linked to the same water and power you've been fighting for. So the next pressure point is obvious. How do you feed a crew for 1,000 days on a planet with toxic dirt, weak sunlight, and no natural ecosystems without turning every meal into a countdown timer on your remaining Earth-shipped rations? On Mars, every meal is a logistics problem first and a cooking problem second. An active adult needs around 2,500 kilocalories per day, give or take. Over 1,000 days, that's about 2.5 million kilocalories for one person. If your stored food averages 4 kilocalories per gram, you're talking more than 600 kilograms of dry food per person, roughly 1,300 pounds. For 6 people, that's several tons, not counting packaging, storage containers, and the volume they take up. You'll absolutely bring a lot of pre-packaged food. That's your initial safety margin. But if you rely only on shipped rations, every future increase in crew size, every extra year you stay, is chained to launch windows and cargo budgets back on Earth. That is not a colony, that's a very distant camping trip. So you have to start growing some of your food locally, even in the first 1,000 days. Not because it's easy, but because the math on mass and calories forces you into it. Every kilogram of food you can produce on Mars is 1 kilogram you don't need to launch from the bottom of Earth's gravity well. The first problem is obvious as soon as you look outside. The ground around you is not soil in any Earth sense. Martian regolith is crushed rock, dust, and minerals. It has no organic matter, no humus, and its microbial life, if any, is unknown and not something you want inside your greenhouse without serious testing. On top of that, it may contain toxic compounds like perchlorates and possibly problematic levels of some metals in places. On Earth, soil is a living ecosystem, full of bacteria, fungi, insects, and decaying plant matter. On Mars, the dirt is basically a sterile, reactive substrate. So early farming won't mean walking outside and planting potatoes in a field. It will mostly be hydroponics or aeroponics, roots in nutrient-rich water solution or sprayed with mist inside a controlled, pressurized greenhouse. You might use treated regolith as an inert support medium after washing and baking it, but the nutrients and the biology will come from you. That means processed human waste, composted plant material, and fertilizer shipped from Earth. You have to build that ecosystem from scratch. You decide which microbes to introduce to help with nutrient cycling. You decide how to balance nitrogen, phosphorus, and potassium in your solutions. If something goes wrong, like a pathogen or an imbalance, there is no natural soil web to buffer it. Your plants can go from fine to dying in days if you miss a sign. Even if you get the chemistry right, you still have to fight the physics of light and area. High-performance greenhouses on Earth can reach impressive yields, tens of kilograms per square meter per year for fast crops like leafy greens, maybe a few kilograms per square meter per harvest for staple crops like wheat or potatoes. But that's with strong, steady sunlight or powerful artificial lighting, and with decades of optimization. Mars sits farther from the sun, so the maximum sunlight at the top of the atmosphere is only about 43% of what Earth gets. Dust in the air cuts that down further, and storms can reduce surface light by 80 to 90% for days or weeks. You cannot trust natural sunlight as your only source, so you pack high-efficiency LEDs and design your farms around artificial lighting. Your crops now depend directly on your power grid. Want to double potato output? That's not just more trays, that's more electrical capacity. Every extra square meter of growing area means a specific number of watts, for a specific number of hours per soul, multiplied across weeks and months. In the first 1,000 days, a power failure in the greenhouse is not just an inconvenience. If the lights go out repeatedly, or the pumps fail or temperature control breaks, plants die. When plants die, you don't just lose those calories, you lose the future seeds, the oxygen contribution, and the crew morale boost. A blackout becomes a delayed famine. 3 or 6 months down the line, when your stored rations were already counted on as backup, not primary food. Meanwhile, the biology inside your greenhouses and tanks is doing its own thing, whether you like it or not. Any closed, warm, humid environment is perfect for microbes. Some of them you want. Bacteria that help to break down waste, microbes that support plant roots, yeast cultures for food production. Others you definitely do not want. Mold that coats surfaces and chokes plants, pathogens that make people sick, biofilms that grow on pipes, sensors and walls. On the ISS, even with strict cleaning routines and small volumes, biofilms still grow on equipment and in water systems. On Mars, your greenhouses and life support bays have more volume, more humid corners, more nooks where condensation can form, and fewer spare parts. Sterilizing an entire greenhouse is not simple when you need the crops inside it, so you end up running an ongoing microbiology experiment whether you plan to or not. You swab surfaces, you test air and water, you track which organisms are present and how they change over time. You may need UV sterilizers, chemical flushes and careful zoning, dirty areas for waste processing, clean areas for sensitive crops, with controlled airflows between them. If you get that wrong, a single mold outbreak can wipe out a major fraction of your food production and force you back onto shipped rations you were trying to save. Behind all of these technical details, there is a human effect that doesn't show up on mass budgets or yield graphs. Fresh food hits your mind much harder than your stomach. Studies from Antarctic stations and the ISS show it clearly. People on long missions crave fresh textures and flavors. Crunchy lettuce, a real tomato, a new herb. When crews grow even a small amount of fresh produce in orbit, the emotional reaction can be intense. It's not about the calories, it's about contact with something alive that you created in a hostile place. On Mars, during your first 1,000 days, communication delays are long, the landscape outside is cold and repetitive, and every system around you is loud, mechanical, and fragile. In that setting, the first bite of a potato that grew in Martian gravity, under your LEDs, watered with ice you pulled from the ground and cleaned yourself, can hit harder than any video call from home. It's proof that the loop closes, that the planet can be made to support you even a little. Food is energy, but it's also culture. How you eat, what you celebrate with, who cooks, who experiments with the first Martian recipe, all of that shapes crew dynamics. A greenhouse failure isn't just losing vegetables, it's losing a big piece of normal life. And that can push stress and conflict up when you can least afford it. So by the end of the first 1,000 days, if you're still there, still eating partly from your own harvests, you've done more than grow lettuce under glass. You've proved that a small artificial ecosystem can stay stable enough in Mars conditions to feed humans at least a little. That's a huge step, but you're still doing it inside thin cans, under fragile domes, in structures never tested for decades of use. And the planet around you is still trying to pull those structures apart with pressure differences, temperature swings, dust and impacts. You're not just living in a house, you're living inside a stressed pressure vessel sitting on alien ground. So the next challenge is obvious and unforgiving. How do you turn thin-walled metal and plastic into something that can act like a real home? When a tiny leak, a bad weld, or a single rock from space is all it takes to end the entire mission in minutes. On Mars, your house is not a building, it's a pressure vessel, and the physics does not give you any slack. Every habitat module is basically a small submarine flipped inside out. High pressure inside near vacuum outside. Inside, you're holding maybe 70 to 100 kilopascals of air. Outside, you have around 0.6 kilopascals. That difference acts on every square meter of wall as a steady, constant load. When you make a cylindrical module bigger, you don't just get more space, you multiply the total force trying to blow that cylinder apart. So the structural math is unforgiving. Thin metal skins, composite shells, and internal ribs are all working full-time just to keep shape. The bolts around a hatch, the welds at panel joints, the bonded seams in inflatable sections, all sit under continuous tension. A minor leak you might ignore in a normal house, like a slow draft around a window, is fatal here. Even a tiny pinhole can slowly bleed pressure. If you don't catch it, alarms start going off. and you are chasing a falling pressure gauge trying to find the source before the atmosphere in that module drops below safe breathing levels. In the first 1,000 days, most of the leaks you see will be the ones nobody predicted. A spot where two materials expand differently in the cold and open a gap. A cable penetration that was sealed fine on Earth but shrinks on Mars nights. A fastener that vibrated loose during landing and only starts leaking after a few dozen door cycles. You'll spend real time with leak detectors, smoke sticks, and ultrasonic sniffers walking through corridors hunting down air that's going missing molecule by molecule. But keeping one can intact isn't enough, because any single volume can fail fast. You need a way to lose part of your home and still live. Redundancy here is not just backup pumps on a single loop, it's redundancy in 3 dimensions. You need multiple separate pressurized zones, with hatches and bulkheads between them. If a fire starts in one lab, you must be able to seal that lab, vent it or flood it with inert gas if needed, and keep the rest of the base pressurized and breathable. If an impact punctures a wall, you need to close interior doors fast, isolate the damaged area, and keep living in what's left. That means extra airlocks, extra internal doors, extra piping and cabling routes. Maybe each main module has at least some independent life support capacity, its own fans, its own CO2 scrubbers and emergency water. Every added wall or hatch costs mass, volume and complexity, but in the first 1,000 days you simply cannot accept a base designed around single-point failures like, if this one connector fails, everyone dies. Later, when there are big settlements, you can spread risk across whole neighbourhoods. Early on, you have a handful of connected cans, and you're always aware that losing even one is a big hit. While you're worrying about pressure and fire, another threat is coming straight out of the sky at random intervals: impacts. Mars has a thinner atmosphere than Earth, so more small meteoroids survive their flight down. Most still burn up or break apart, but the cut-off size is different. A rock that would never reach the ground on Earth can make it all the way to the surface on Mars. You're betting your life that nothing the size of a fist or a brick hits your pressure hull at tens of kilometers per second. The odds for any single square meter per year are low, but they are not zero, and they climb as your base spreads. One hit in the wrong spot at the wrong time could open a high-rate leak or structurally damage a section of the habitat. That's why burying modules under regolith becomes a priority. A couple of meters of soil above you will shred or slow most small debris before it ever gets near your metal walls. In the first 1,000 days, though, you're still in the transition phase. Some modules may be only lightly covered. Some might still be exposed while excavation gear is being tested and adapted to the terrain. Your first months and years are when you are most exposed to this low probability, high consequence risk. Even if nothing ever hits you from above, your materials are under long-term attack from the planet itself. Pressure cycling from small fluctuations, day-night, temperature swings that can span tens of degrees, dust abrasion on the outside, humidity on the inside, and radiation everywhere, all combine to age materials in ways we have not fully seen. We have data from Mars landers and rovers that shows metals and plastics can last for a decade or more, but those are static machines, not human habitats with people slamming doors, bumping equipment, and breathing out moisture. You're going to learn which rubber seals get stiff and crack at -80 degrees Celsius, which plastic windows yellow or craze under radiation, which paints flake when exposed to dust storms, and which alloys start to corrode when Martian dust mixes with condensation and human sweat at surface joints. Outgassing is another issue. Some interior materials slowly release chemicals into the air. In a closed habitat, that can build up and affect crew health or sensors. You will end up cataloguing which floor coverings, wall panels, foams, and adhesives behave well after a year, and which need to be banned from future designs. On top of structural survival, you have to think about what it's like to actually live inside this machine. Your habitat is not just a shell, it is your entire visible, breathable world. Ceiling height, corridor width, lighting colour and intensity, noise from fans and pumps, all of it feeds directly into how people feel and perform. Data from submarines and Antarctic stations is clear. Cramped, noisy, monotonous spaces raise stress, increase conflict, and can feed depression and sleep problems. In your first 1,000 days, your entire city might be 300 square meters of pressurized floor area, around 3,200 square feet for 6 people. That's less than many small houses, but sliced into labs, bunks, hygiene modules, airlocks, storage, and machinery rooms. Privacy is thin, quiet corners are rare. You'll be adjusting lighting schedules to simulate a healthy day-night rhythm, choosing wall colours to avoid that permanent white box lab feeling, and trying to isolate noisy equipment behind sound barriers. Even minor choices matter, whether crew quarters have doors or curtains, how much headroom people feel when they stand, whether they can see even a small view of outside or only screens. You will see firsthand which layouts create friction, where people collide in tight corridors, which rooms everyone avoids, and which spots become unofficial social hubs. So during these first 1,000 days, you're not just trying to keep air in and rocks out. You're running full-scale experiments in structural engineering, materials science, interior design, and human psychology, all at the same time, with no option to move to a better apartment if you get it wrong. And all of this still depends on one thing you don't control directly: power. Your pressure hull, your heaters, your pumps, your CO2 scrubbers, your lights, your greenhouses, your drills, your rovers, all of it dies the second the energy flow stops. On Earth, if the power goes out, you get cold and annoyed. On Mars, if the power goes out and stays out, you suffocate or freeze. So the next pressure point is as hard as it gets. How do you chase every single electron you can get on a planet with weak sunlight dust storms that turn day into twilight and nuclear units that are compact but finite and build a power system that won't quietly kill you somewhere around day 600? On Mars, power is not just utilities, it is the limit on everything you do. Mars orbits about 1.5 times farther from the Sun than Earth, around 1.5 astronomical units. That means it receives only about 43% of the solar energy per square meter that Earth does. A panel that might give you 200 watts per square meter at noon on Earth might only give you 80 to 100 watts per square meter at noon on Mars in clear conditions, with clean glass. Now factor in dust. Panels get coated day after day, even a thin film can knock output down. During a dust storm, available sunlight can drop by 80 to 90%, so the 80 to 100 watts number can crash into the single digits. Say your base needs around 20 kilowatts of continuous power to run life support. Heating, computers, lighting, pumps, comms, basic science, and a little margin. To get that on average from solar, with losses and storage, you are fielding hundreds of square meters of panels, maybe into the low thousands, plus a large battery bank. In your first 1,000 days, there is no big automated construction company doing this for you. You and your robots are hauling panels out of cargo bays, unfolding them, bolting them down, running cables, and checking connections, mostly by hand. What you end up with is a fragile, dust-covered power farm stretching out from your base, where a single bad rover maneuver, a small slide, or a disconnected cable can quietly take out a big fraction of your generation. You will walk those rows, brushing panels, checking junction boxes, tightening mounts, because every watt you can claw back is another bit of safety. Solar alone is a risk, so you look for something more cool, nuclear. But that comes with its own set of limits. A small fission reactor in the 10 to 40 kilowatt electrical range is a game changer on Mars. Concepts like NASA's kilopower show that compact reactors can deliver steady power, day and night, through dust storms, with a small footprint. Put 1 or 2 of those near your base, shield them properly, and suddenly the worst solar storm is a lot less scary. But getting nuclear material off Earth is technically heavy. Launch failures with radioactive cores are a major concern and regulations are strict. Early missions might only be allowed to carry 1 or 2 such units. If one fails to start or has to be shut down for any reason, your planned power margin collapses. So you learn fast what non-essential really means. You start triaging your own electricity, Do you cut back greenhouse lights today to keep more battery reserve for a predicted dust event tomorrow? Do you postpone running a high-power metals furnace so you can refill water tanks? Do you shut down some lab experiments for a week to give the life support processors more room to operate? Power planning becomes a daily strategic decision, not something you leave to a utility company. Even if you can generate power, you still have to store it. And Mars makes that part difficult too. Most likely you're relying heavily on lithium-ion or similar batteries. Those batteries hate deep cold. When temperature drops, their capacity falls, internal resistance climbs, and their useful cycle life shrinks. Leave them too cold for too long and you damage them permanently. So you have to keep your battery banks within a comfortable temperature window, maybe with heaters and insulated enclosures. But heating batteries uses power, which is exactly what you're trying to store. It's a feedback loop. You spend energy to keep the things that store energy alive. You can also store energy in chemical form, like hydrogen or methane produced by running electrolyzers and reactors when you have excess power. That stored fuel can later drive fuel cells or generators. But every conversion step has losses. Electricity is to hydrogen, hydrogen to methane, methane back to electricity. Each step throws away a percentage of the energy as heat. You add more hardware, some more pipes, more safety systems, and more points of failure. In your first 1,000 days, your energy system feels like a chain of buckets with holes in them. Solar panels feed batteries feed heaters and life support, reactors feed the base and top-up storage, and every part has inefficiencies you have to live with. The numbers never feel generous. When supply and storage get tight, you face decisions that would be unthinkable on Earth. Life support is not negotiable. Air circulation, CO2 scrubbing, minimal heating, water processing, core computing, and communications stay on. Everything else gets pushed onto a list. On that list are greenhouse lights, mining rigs, lab freezers, 3D printers, non-critical rover charging, entertainment systems, even heating in less used habitat modules. There will be nights in those first 1,000 days when you go to sleep knowing that if the next few sols are unusually cloudy, or if one more piece of power hardware fails, you will have to make cuts you really don't want to make. Maybe you dim greenhouse LEDs and accept slower plant growth. Maybe you shut down part of the workshop and delay making spare parts for something else. Maybe you close off a module and let it get colder to save heating. You're always a few bad days away from that kind of rationing, until your generating and storage capacity grows far beyond your basic needs. Early on, you live in the narrow band where luxury is not hot showers and big screens. Luxury is enough margin that a dust storm doesn't immediately trigger an emergency meeting. If you make it past those first 1,000 days, the picture can start to change. Once survival is under control, power stops being just about staying alive and becomes the key to expansion. Smelting regolith into metals takes a lot of energy. Running large-scale greenhouses or vertical farms takes energy. Manufacturing, electrolysis on industrial scales, even large computing clusters all pull serious power. At that stage, you're talking about tens or hundreds of kilowatts, eventually megawatts, and building something that looks more like an industrial grid than a fragile outpost system. But in the early phase, you're building the backbone of that future grid by hand. You carry panels, you hand-bury cables in shallow trenches, you position small reactors on stable ground and lay out heat rejection systems. A single misrouted cable, a short caused by dust and moisture where you didn't expect it, or a rover cutting through a line while towing equipment can knock out a large fraction of your generating capacity in one move. So during your first 1,000 days on Mars, power is a constant tight constraint behind every choice. How many EVs you schedule, how many experiments you run, how fast you expand, even how bright your lights are at dinner, all pass through the same bottleneck. Do you have the watts to support that? And while you're fighting to keep the electrons flowing, another enemy is working slowly but relentlessly on the machinery that handles all of this. Dust, corrosion, and wear. Every suit, rover, pump, and panel is grinding its way toward failure in an environment that was never gentle to machines in the first place. So the next question is ugly and very practical. How do you keep your hardware alive when every moving part is eating dust, every surface is oxidizing, and your spare parts shelf is a fraction of what you truly need for 3 brutal years. On Mars, dust is not a background detail, it is one of your main enemies. Martian dust grains are tiny, jagged and clingy. They're not smooth like beach sand that's been rolled by waves. They've been broken by impacts and freeze-thaw cycles, so their edges are sharp at the microscopic level. Every hinge, zipper, latch, and rotating joint in your suit is constantly getting hit with this mechanical sandpaper. On the Apollo missions, lunar dust got into suits and hardware so fast that in just a few days, seals started degrading and joints got stiff. Those missions were short, with only a handful of EVAs. On Mars, you're planning for years of daily or near-daily surface work. That means thousands of hours of suit time, rover driving, sample handling, and outdoor construction. Early suit designs will use bearings, seals, and fabric layers that have only been tested in labs and short field trials. The real failure modes will show up only after long exposure. Zippers that stop sealing, bearings that grind themselves flat, visor mechanisms that seize because dust has packed into the tracks. Rovers will see wheel hubs filling with grit, steering joints wearing out faster than expected, suspension components scoured by constant dust splash. You will learn very quickly which designs were optimistic. Maintenance-free parts on the spec sheet will turn into weekly inspection in the real checklist. You will start adding dust covers, extra shields, and new cleaning steps on the fly, just to keep essential gear moving. The trouble is, the dust doesn't just scrape, it also charges. Mars is bone dry. There is almost no humidity to bleed off static charge. As dust grains rub against each other in wind and storms, they pick up electric charges through triboelectric effects. That means dust clouds and even individual panels and suits can build up significant voltage differences relative to their surroundings. Static discharges can quietly damage electronics, punch through thin insulating layers, and cause weird sensor glitches. A small spark you never see can flip a bit in a memory chip, cause a reset in a control board, or slowly weaken a dielectric until it fails later. In extreme cases, if charge builds up enough, you could even feel shocks on equipment or see corona effects in low-pressure environments. On Earth, moisture in the air helps equalize charges. On Mars, you have to design grounding and shielding much more carefully. Suits need paths to bleed, charge off safely when they dock back in airlocks. Rovers need bonding straps and grounded frames. Panel arrays and external structures need grounding networks that can handle strange current paths through dust-coated surfaces. The first time a dust-driven static event takes down a major subsystem, maybe a communications relay, a power converter, or a life support controller, that incident will be studied for years. It will change design standards for every future Mars habitat and robot. But in your first 1,000 days, you're on the sharp end of that learning curve. On top of the mechanical and electrical attacks, the dust brings chemistry problems of its own. Martian soil in many locations includes perchlorates, reactive chlorine-oxygen compounds. Under ultraviolet light and radiation, these can break down into even more reactive species. Those can corrode metals, attack coatings, and degrade polymers over time. That means the same dust that scratches your suit visor can also slowly chew on the suit layers, the seals around your habitat windows, and the linings of your irrigation pipes in greenhouses. You can simulate some of this on Earth with Mars analog dust and UV lamps, but you cannot fully reproduce real Martian conditions, the exact dust composition at your site, the radiation spectrum, the full temperature swings, and the constant cycling between inside and outside environments. So you'll run long-term materials tests in situ. You'll leave sample plates outside for months, checking how different alloys, coatings, fabrics, and plastics age. You'll cut apart failed parts and look at the cross-sections under microscopes in your lab to see where corrosion started, where cracks grew, and how dust packed into microgaps. That data will feed into the next generation of hardware designs, but again, that means you are discovering the problems by experiencing them. All of this adds up to one big fact about your daily life. Maintenance is not a side task, it is a full-time job. On the ISS, astronauts already spend a big chunk of their time just maintaining systems, filters, pumps, valves, laptops, exercise machines. On Mars, take that baseline, then multiply it by harsher environment and extreme distance from spare parts. Your first 1,000 days will feel like living inside a car that is always on a long road trip with every warning light blinking on at different times, and the nearest repair shop is a planet away. Fans start making new noises, so you pull them, clean them, and put them back. A rover starts drawing more current than usual, so you strip the wheel assembly, clean dust out, re-grease, reassemble. A suit joint starts feeling stiff, so you schedule it for teardown, inspection, and seal replacement. Checklists dominate your schedule. Weekly inspections of external cables, monthly checks of pressure fittings, daily walks around the power field to spot tilted panels or damaged mounts. Every time you skip something because you're tired or busy, you raise the odds that a quiet wear problem turns into a sudden failure later. A stuck valve that chokes off water flow, a jammed suit bearing that fails during an EVA, a clogged radiator that overheats a key system. You will get very good with tools. You'll improvise fixes with what you have. You'll remachine parts on 3D printers and small mills. You'll figure out how to extend the life of components that were never designed for repair at all. Every successful patch buys you another week, another month of operation. Every missed crack or unlubricated joint sets up a future emergency. While you're doing all of this, you're also writing the blueprint for better hardware you don't have yet. The pain points you hit in those first 1,000 days will define version 2.0 and 3.0 of almost everything. Engineers back on Earth will see your failure reports and redesign suit joints with fully sealed bearings, pick new alloys that resist perchloric corrosion, build dust-resistant fabrics that don't clog as easily, and develop self-cleaning solar panels that use vibration or electrostatics to shed dust. But you won't have those upgraded systems for most of your first mission. You are the destructive testing phase for civilization's Mars equipment. Your suits, rovers, drills, valves, and panels are the early batch that shows where the designs break. So while the planet quietly eats your machines, you keep them going through skill and constant work. But this war with dust and corrosion is only one layer of stress. There's another limit you can't fix with a wrench: the speed of light. No matter how good your tools are, no matter how detailed your procedures are, Earth is always between 4 and 22 minutes of radio time away. That delay doesn't just affect data. It reaches deep into how decisions are made, how emergencies play out, and how isolated you feel when something goes wrong. So the next question cuts through everything else. How do you run a base, solve failures, and stay human when your home planet is always at the far end of a conversation you can never have in real time? On Mars, the speed of light is fast, but not fast enough to make you feel any less alone. The distance between Earth and Mars swings from about 55 million kilometers to over 400 million kilometers, roughly 34 to 250 million miles as the planets move in their orbits. That translates into one-way communication delays of about 4 minutes at best, and up to around 22 minutes at worst. Round trip, that's 8 to 44 minutes, so there is no real-time conversation, no live back and forth. You cannot call mission control and have a normal chat. When something in your habitat starts behaving strangely, you can send data and you can ask, "What do you think this is?" But by the time an answer comes back, half an hour might have passed, and the situation has already changed. That means, in practice, you become your own mission control. Earth is a consulting office you email, not a live help desk. You and your crew have to read the alarms, interpret the graphs, and choose actions on your own timeline. Training covers a lot, but it can't preload 3 years of specific failure cases into your brain. At some point, you're staring at a screen with numbers that do not match any sim you've seen, and there is no one who can talk you through it in real time. The same delay kills the idea of driving things from Earth like a video game. On the Moon, with about 1.3 seconds of delay one way, teleoperating rovers from Earth is hard but doable. You push the joystick, wait a bit, see the result, correct. On Mars, a 10 or 20 minute delay means if you turn the wheel left and the rover starts sliding toward a crater edge, you don't see that until long after it has either stopped or gone over the side. Direct joystick control is impossible. So your surface robots must be semi-autonomous. They need onboard software smart enough to handle hazards, navigation, and basic tasks without constant human microcontrol. They can get high-level commands from Earth, but the moment-to-moment decisions have to happen on Mars, either in the robots themselves or via local operators working with fast links. That pushes responsibility onto you again. You are the one who physically walks out to a stuck rover. You're the one who swaps its wheel motor, reseats its antenna, or reboots a frozen controller with a hardware jumper. The first 1,000 days are the transition period where Mars stops being a remote-controlled robot playground and starts being a place where real, on-site human operators and mechanics take over. An Earth-controlled outpost becomes a Mars-based agency because the physics gives you no other option. This delay doesn't just hit operations, it hits your personal life. Relationships back home turn into a stream of text messages and recorded clips. You send a video and you know they'll see it minutes later at best. Maybe much longer if it's queued or the link is busy. They reply, and by the time you watch it, your day has moved on. There is no live call where you react to each other's tone in real time. Arguments can stretch out over days, not because anyone wants that, but because every back and forth step has a built-in pause you can't erase. If something urgent happens on Earth, a crisis, a family emergency, a global event, you don't hear about it instantly. News arrives delayed and bundled. By the time you see it, the situation might have already changed again, but you won't feel that change directly. If something urgent happens to you, a sudden failure, a medical emergency, Earth can't do much more than watch data come in and send advice that arrives after you've already acted. Studies from polar stations and long-duration space flights already show how isolation and communication limits affect mood, sleep, and performance. Mars adds a hard physical rule on top of that. You can't pay for a faster plan, you can't launch a better satellite. Light moves at one speed, and you're too far away. That hard barrier reinforces the feeling that on a deep level, you and your crew are on your own. In that environment, decision-making feels very different from anything in Earth orbit. During Apollo, if instruments looked strange, you had dozens of people in Houston running calculations, checking procedures, and feeding options back to the crew within seconds. On the ISS, if something weird happens, you can talk to ground in almost real time. On Mars, you are the one in front of the console when a reactor temperature creeps out of normal range, or an air sensor starts drifting, or a pressure curve in a habitat wall doesn't match yesterday's log. Do you evacuate a module now, or watch it for another hour? Do you shut down a nuclear unit on a suspicious reading and accept the power hit, or assume it's a sensor error? Do you send people outside for an unscheduled EVA to check a suspected leak in the middle of a dust event, or wait until conditions are better? In your first 1,000 days, procedures are early and incomplete. Simulations are based on limited data. Real Martian logs are still short. You will be making calls that affect not just your crew's safety, but the future rules for every mission after you. If you push too hard toward caution, you might cripple your base's growth. If you push too hard toward risk, you might trigger the first major accident on another planet. Either way, you make those choices with less information than you'd like, and no one in your ear saying, "We ran the numbers, here's the answer." Over time, that reality starts to shift something bigger than just protocols. It starts to shift culture. In the early days, almost every big decision still flows from Earth. Funding, mission goals, base layout, crew selection, high-level safety rules, all of that comes from agencies and companies back home. Culturally, Earth is the capital, Mars is the field site. But every delayed conversation where you solve a problem before the answer arrives, every emergency you handle without waiting for permission, every procedure you write locally, because nothing from Earth fits the situation, moves the center of gravity a little. Mars starts to become a place that makes its own calls, writes its own standards, and pushes its own priorities. You and your crewmates in those first 1,000 days are the hinge generation. To people before you, Mars is a mission. To people after you, Mars will be a place where kids grow up. You're the group that lives through the transition from "we do what Earth tells us" to "we figure it out here and then inform Earth what we did." That independence is necessary, but it comes with a price. You are isolated, under pressure, and constantly asked to act like both the crew and the ground team at the same time. The planet is trying to kill you. The systems are immature. The light speed delay is absolute. All of that lands on human minds that were shaped on Earth, in big societies with easy escape valves, walks outside, new faces, different cities. On Mars, for the first 1,000 days, your entire social universe is a handful of people in a sealed environment, under rules you can't break without risking everyone. So the next question turns from physics to psychology. How do a small group of humans stay functional, avoid tearing each other apart, and build the beginnings of a real society when there is nowhere to go, no one else to see, and every conflict plays out under the same thin roof that keeps you alive? On Mars, your society at the start is not a city, it's a small group in a box. Early crews are likely 4 to 10 people. That's your entire face-to-face world for 1,000 days. No new co-workers, no casual strangers, no going to a different bar, no weekend away. You wake up, see the same faces at breakfast, work with them all day, see them at dinner, and hear them moving around the habitat at night. We already know from Antarctic winter-over crews and long-duration ISS missions that small, isolated groups under stress see more conflict, more depression, more sleep problems, and a pattern called the third quarter effect, where after the halfway point, morale often drops hard before it recovers. And that's in places where, in a true emergency, evacuation is at least possible. On Mars, there is no emergency ride home. Once you land, you are committed for the full arc of the mission. That knowledge sits in the back of everyone's mind. Arguments are never fully small because in a 6-person crew, a 2-person conflict is 1/3 of the population. You can't rotate out teams, you can't just separate people into different buildings in different cities. The social network is tiny and tightly coupled. On top of that, even your sense of time is under pressure. A Martian day, a sol, is about 24 hours and 39 minutes. That extra 39 minutes per sol sounds like nothing, but your internal clock, your circadian rhythm, is tuned to roughly 24 hours. Lab experiments show humans can stretch a bit, but not indefinitely without help. If you just free run going to bed later and later each sol, you drift relative to the external day-night cycle. You start waking when the sun is up at weird times, working when your body wants to sleep, and you slide toward a kind of chronic jet lag. So you need strict lighting and schedule control. Lights in the habitat shift colour and intensity to cue morning, day and night. Work and sleep blocks are set to keep everyone roughly synced. You might anchor the schedule closer to Earth days or to Mars sols, but either way the timing has to be managed. If you let everyone drift on their own, you end up with people out of phase, some tired during critical tasks, others awake and restless when everyone else is trying to sleep. Over months and years, that can feed into mood swings, mistakes and conflict. And when conflict happens, there is nowhere to really go. On Earth, if an argument blows up, you can walk out, take a drive, go for a long walk, see other people, or just change locations. On Mars, away is a few meters of corridor and maybe a different module. Going outside is not a casual option. It's a scheduled EVA with a checklist, a suit, and a safety plan. You can't storm out of the hab and wander off to cool down. That means social tensions have nowhere to dissipate except within the same sealed system. Small annoyances build because there is no automatic reset. Someone's eating habits, noise at night, work pace or attitude can grate more and more when you see it every day and can't escape it. Selection and training help. You pick people who are stable, cooperative and skilled at conflict management. But selection cannot remove human nature. The first serious interpersonal breakdown on Mars, a crew member who refuses to work with another, a romantic entanglement that goes bad, a person who stops following group norms, will be more dangerous than many technical failures. A broken pump can be replaced. A broken team might not be fixable with any tool you brought. And mental health support is limited by physics and maths. Therapists are on Earth at the far end of multi-minute delays. You can schedule remote sessions, but they are never in real time, and they compete with bandwidth needed for operations and science. You can send logs, feelings and questions. You get advice back hours later. That's better than nothing, but it's not the same as sitting in a room with someone who can read your body language and respond instantly. Medications are limited to what you flew. You have a finite pharmacy, antidepressants, anxiolytics, sleep aids, maybe some antipsychotics in case of extreme events. Every prescription is a trade. Will this person need this drug long term? What are the side effects in partial gravity and high radiation? What happens if we run out? You cannot just try a different medication easily, because you might not have it. VR, movies, games, music, conversation with Earth. All of that helps, but it is still happening in the same rooms, with the same background hum of fans and pumps, and the constant awareness that outside the wall is near vacuum and lethal cold. You're asking human brains to cope with chronic danger, sensory monotony, very tight social circles, and heavy responsibility. The first 1,000 days will force space agencies and doctors to rethink what mental health support has to look like when evacuation is impossible. Peer counselling, group check-ins, mandatory rest cycles, and quiet hours won't be nice extras. They will be core safety systems. At the same time, something new is forming inside that pressure cooker. Culture. Every little tradition your crew starts becomes part of the foundation for a Martian society. Maybe you have a weekly shared meal where everyone cooks something from their home country. Maybe you mark the Sol of Landing as a local holiday. Maybe you have a ceremony for the first plant harvest, or for someone's birthday. Those are not small details. They are prototypes for future public holidays and rituals. The first time someone dies on Mars, how you handle it, memorial, burial, or cremation, what you do with remains in a closed system, will echo through future generations. The way you name features outside the habitat, the jokes you make about local hazards, the slang you develop for tools and places, all become part of the Martian accent future crews learn. Your in-jokes, your little rituals before an EVA, your crew traditions around movie night or first taste of fresh lettuce are the beginnings of a culture that did not exist before. The hardest, most stressful days are the ones that write the myths later generations will repeat. Back in the first 1,000 days, they had to work. So inside this small social bubble, you're not just trying to avoid breakdown, you're also setting patterns. How you solve arguments, whether leadership is rigid or shared, how much room individuals get to be weird or non-standard, all of that shapes what Martian society will mean later. But building a functioning mini-society under glass still doesn't make you independent. As long as you import nearly everything from Earth, you're an outpost, not a civilization. To cross that line, you have to start making things from local materials, metals, plastics, fuel, bricks, replacement parts. You have to move from repair shop to factory floor, even if that factory is small and spread across a few dusty modules. So the next escalation is economic and technical. How do you turn a set of tools and 3D printers and a pile of regolith into the beginnings of a Martian industry, when every machine you run and every process you test adds one more way the planet can hurt you in those same first 1,000 days? On Mars, you quickly find out you did not land a civilization, you landed a toolkit. Launching a single kilogram to low Earth orbit costs thousands of dollars. Sending that same kilogram all the way to Mars with transfer stages and landing systems costs even much more in fuel, hardware, and planning. There is no way you're importing an entire industrial base, foundries, factories, assembly lines, and warehouses full of spares. What you actually land is a starter kit. A few metal and polymer 3D printers, some CNC machine tools, small furnaces, basic chemical reactors, a modest lab for materials analysis, maybe a compact pilot plant for making propellant. It's enough to repair what you brought, make simple parts and run small experiments. It is not enough to build anything you want from scratch. Your job in the first 1,000 days is to push that starter kit as far as it can go. You have to move from "we fix things that break" to "we can manufacture at least some of the things we need from Martian regolith water and atmosphere." That shift, from repair shop to light industry, is what starts breaking your long-term dependence on Earth. To do that, you have to take something that's been a buzzword for years, ISRU, in situ resource utilization, and turn it from a handful of demos into a full-link system that keeps you alive. Before humans arrive, we test single pieces. Extract oxygen from CO2 with a unit like MOXIE. Heat simulated regolith in ovens to release trapped water. Press bricks from fake Mars soil in labs. Those tests prove that each step is possible. On Mars, you have to connect them. You dig regolith with real bulldozers and loaders adapted for 0.38 G. You run it through crushers and sieves to get the right particle sizes. You bake some of it to pull out water. You separate useful minerals, iron-rich fractions, silica-rich fractions, maybe sulfates and carbonates. You cast blocks for radiation shielding and foundations. You smelt metals in small electric or solar-driven furnaces. Every step has a cost in energy and wear on machines. Every kilogram of metal you produce locally is one you don't have to launch, but to get that metal you burn power you might have used for food or life support margin. The mass balance is tight too. Reactors, crucibles, filters and electrodes all have limited lifetimes, and you don't have infinite spares. So your first 1,000 days are the debug phase for planetary scale ISRU. You will learn which processes are practical in this environment, which ones eat too much power, which ones create toxic byproducts you can't yet handle, and which ones actually deliver useful hardware at the scale you need. 3D printing looks like a magic solution from afar, but on Mars it comes with its own set of Mars-specific problems. On Earth, metal and ceramic additive manufacturing already work. Printers use carefully prepared powders or wires with controlled particle size distributions and known compositions. You input a design, tune some parameters, and get a usable part. On Mars, your feedstock is ground up local rock and soil. The base material might be ancient basalt shattered by impacts mixed with sulfates, oxides, and traces of other minerals. The particle sizes coming out of your crushers and mills won't match ideal Earth powders without serious processing. Impurities change melting points, flow behavior, and strength of the final part. Vacuum or low-pressure sintering behaves differently than in Earth's atmosphere. So you spend a lot of time tuning printers, running test coupons, and breaking them in your lab to see what you actually made. You'll print simple shapes from locally derived powders, test their tensile strength, fatigue behavior, and thermal expansion, and compare them to spec. Sometimes you'll find that a part you thought was fine cracks under real load because a hidden void or impurity acted as a flaw. Those failures teach you how pure your powders need to be, how fine you have to grind, and what binder or process changes are needed. At the same time, you're starting to set up what are, in essence, small chemical plants inside or just outside your fragile habitat. Fuel synthesis, plastics production for seals and pipes, fertilizer manufacture for greenhouses. All of those require reactors that run at high temperatures and often high pressures. You might be making methane and oxygen from water and CO2, producing simple polymers from imported precursors and local gases, or concentrating nitrates and phosphates from processed regolith and waste streams. On Earth, those systems sit in large industrial zones with big safety clearances, thick walls, and dedicated emergency crews. On Mars, they sit in or next to thin-walled pressure vessels in a low-pressure, dusty, freezing environment. Everything around them is packed with other life-critical systems. If a reactor leaks toxic gas, it leaks it into your small, shared air volume. If a high-pressure line fails, it can damage nearby equipment that you cannot easily replace. Safety margins have to be huge, but your available mass and volume are small. You'll over-engineer containment vessels and pressure relief systems as much as your payload budget allows. You'll run processes at lower pressures or temperatures than ideal just to cut risk, sacrificing efficiency for safety. And even with all that, the first industrial accident on Mars, a runaway reaction, an overpressurized tank, a feed line failure, will reshape design codes for decades to come. If you survive long enough and if your industrial experiments mostly work, the role of Mars in the larger human system can start to change. In the long run, Mars might export high-value products that are cheap to make there or uniquely suited to space. That could mean rare isotopes produced in reactors, specialty alloys or composites formed in low gravity, software and data products developed by local experts, or even components manufactured for use elsewhere in the solar system. Physical bulk commodities shipped uphill from a gravity well aren't likely early exports, but high-value density items are. None of that is relevant in your first 1,000 days if you can't even make your own spare pump housings and simple structural parts. The future where Mars sends products outward rests entirely on whether this early phase can turn "we're barely keeping the lights on and patching leaks" into "we can reliably produce the pieces we need to expand." So as you run furnaces, tune printers, and debug chemical reactors, you're not just playing factory. You're proving, or failing to prove, that a tiny industrial base can take root in hostile soil. If it works, you've shown that a planet can start bootstrapping itself from dust and ice up to real infrastructure. If it doesn't, every later mission will face the same dependence on Earth and the same narrow safety margins. But even if you win that fight, even if your machines spin up and your base stops feeling like a prototype, there is still one more level to this entire story. It's about why anyone would accept these risks in the first place and what it means if you actually make it past those first brutal 1,000 days. So the final question is the biggest one. Why are the first 1,000 days on Mars the hardest by design? And why do people still choose to go, knowing that if they survive, they will have changed what home planet even means for our species? The first 1,000 days on Mars are hardest because every unknown is stacked at the front, on you. Engineering, biology, psychology, all of them are least certain at the start. Later settlers will get thicker radiation shielding, fully buried habitats, reactors with long track records, life support hardware on version 4, medical kits tuned by real Martian data, and bigger crews spread across multiple sites. You will not. You get thin walls, prototype systems, and a social group small enough that one person having a bad month can shake the entire base. History lines up with that pattern. Early ocean crossings had the highest loss rates. Early polar bases had the worst accidents and the roughest winters. Once routes were mapped, equipment improved and procedures matured, risk dropped. The frontier phase is when most failures happen, because that's when the models are weakest and the surprises are constant. On Mars, it's the same, just with higher stakes. The learning curve on entry, descent, landing, life support, radiation shielding, industry and psychology is steepest in those first few years. You are front-loading the risk curve so that everyone who comes after you stands on something more solid. Statistically, physically, historically, your 1,000 days sit in the danger zone on purpose, and that's exactly why they matter. Because until someone lives through them, the numbers you've heard are just estimates. All the dose rates, failure probabilities, crop yield projections, social stress models, none of them are fully real until a crew runs them in practice. Robots can tell you how much radiation hits a sensor, how strong the wind is, how much water is in the soil. They can't tell you what happens to a human bone in 0.38 G over 3 years, or how many hours of artificial light a tired crew actually remembers to give their plants, or how often people really make mistakes under chronic low-level fear. In your first 1,000 days, your body becomes part of the data set. Your blood work, your bone scans, your EEGs, your sleep logs, your reaction times, your mood surveys, all of that flows back to Earth and feeds into new models. The same for your machines. Every pump failure, every cracked seal, every near miss with power or air or water. Engineers will dissect those events, update designs, and change training. From your side, it feels like constant stress and endless checklists. From the outside, it is one long experiment with civilization-level consequences. You're turning "we think this will work" into "we know," because this is what happened when 6 humans tried it for 1,000 days on Mars. If you make it that far, you don't just add data. You start to crack a deeper psychological barrier. What home means. Right now, home means Earth by default. 1G, blue sky, thick atmosphere, clouds, rain, oceans, forests. Even people who feel disconnected from their country or culture still assume home planet equals Earth. Everything else is visited, studied, maybe mined, but not really home. Survive your first 1,000 days on Mars, and that picture starts to break. Because now there's a place where humans have lived continuously through multiple Martian seasons, under regolith roofs and artificial lights, breathing air made from machines and eating food partly grown in red dust. You have memories anchored there. The view from a certain crater rim, the smell of the greenhouse, the sound of dust hitting the habitat skin during a storm. The real shift happens when someone, maybe you, maybe a later crew member, gets on a transfer ship heading back to Earth and finds themselves thinking, I can't wait to get home, and means Mars. At that moment, home planet is no longer a fixed concept, it's split. Children born later under 0.38 G, who grow up knowing only underground tunnels and domes, will feel as normal in that environment as you do in 1G. That psychological singularity, the first time a person feels homesick for another planet, depends completely on the first waves not dying in year 1. No continuous presence, no new home. Underneath all of this is an even bigger shift in how we think about life in the universe. For roughly 4 billion years, all known life has been locked to one world. Earth looked unique, not just because of its conditions, but because biology and environment were fused. Life here, atmosphere here, gravity here, or nothing. Your first 1,000 days on Mars are direct evidence that this link can be broken by technology. If a small, fragile biosphere, your base, your bodies, your microbes, your plants, can stay alive and stable on a world that started out completely hostile, then habitable stops being just a natural label. It becomes an engineering target. The rest of the solar system, and eventually worlds around other stars, stop being unreachable lights and become locations with problem lists. Radiation to shield, gravity to adapt to, resources to mine, chemistry to manage. Challenging but not inherently off limits. That doesn't mean terraforming overnight. It means this. Once you've run a tiny artificial Earth bubble on Mars for 1,000 days and kept everyone alive, the idea that life must stay tied to one planet is gone. The uniqueness of Earth as the only place life can exist starts to look like a historical phase, not a permanent rule. So why go now, when the gear is rough, the risks are front-loaded, and the comforts are minimal? Because the difficulty is the whole point. You're not going because it's a safe, polished experience. You're going precisely because it isn't. Every scar the colony earns, every broken pump you manage to fix, every dust storm you ride out with the lights at minimum, every argument you patch before it splits the crew, makes it easier for the next wave. In those first 1,000 days, surrounded by cold rock, thin air, and failing prototypes, you are doing something no simulation on Earth can ever copy. You're proving that a small group of humans can take an entire alien environment and force it to support them day after day with no instant backup. You're rewriting what human habitat means, from a planet with an atmosphere to wherever we can build the right systems and survive the learning curve. If you make it to day 1001, the hardest part of that rewrite is already done. The unknowns are smaller. The gear is better. The manuals are thicker. The next crews will still face danger, but they'll be walking in footprints you left, using hardware you helped debug, and living in habitats built on lessons you paid for with sleep, stress, and risk. The first 1,000 days on Mars are the hardest because they have to be. They are the price of turning a cold, indifferent world into a place humans can actually call home, and the cost of proving that our species doesn't have to live and die on the same rock where it started. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.